Welcome.
Hello. Hello. How are you, everyone? So happy to see you.
Please tell us what we have to present to us.
So we're going to talk about how robots are influencing our lives, in particular exploration in space, but also in our everyday environments. I'm really excited about talking about this topic. I have obviously slides to share. So when you're ready, I can just come up.
Please go ahead.
Absolutely. All right, fantastic. Can you all see my slides?
Yeah, perfectly.
Yeah. Okay, so I believe it is a quick succession of talks. There are 15 minutes, so I'm gonna skim through the slides and go quickly. I have to tell you, I'm a big fan of your program. I was born and raised in Barcelona, in Spain, and there is such an incredible synergies in exploration and technology between the Iberian Peninsula, both Portugal and Spain, and this has been going on for several years. I'm extremely happy to be back again here, giving a talk. And I wish I could have been there in person, but I'm in Boston, in a place in Boston Dynamics, where is one of the, probably people know these robots that they do backflips and they do amazing things. I'm a consultant for this company aside from my job of being a faculty, and I happens to be that this week I was here. But nonetheless, I'm with my heart with everyone in Azores, beautiful Azores. And the talk has suggested is, what are these human-centered robots? What are they useful for? How can they solve some of the most important future problems in our society, in our exploratory enterprises as well? And in particular, we call them human-centered robotic systems in the sense that we are looking into creating machines that they can do everything that humans can do. Not necessarily, and I don't want people to think that we're trying to replace people. We're trying to obviously augment people, and we're trying to also allow enterprises and efforts that require physical embodiments that otherwise could never happen if it was not because of the use of robotic systems. And obviously, one of the obvious forms for robotics is having the humanoid form. The humanoid form is the closest form to the human form. It has two arms, it has legs, and because we know that humans as people, we are extremely versatile and we're able to reach everywhere, manipulate, and do a myriad of things, whether it's manufacturing, organizing, maintaining, transporting, and so forth. The humanoid form promises, with the proper AI systems, the proper perceptual systems, and the proper economies of scale, it promises to solve a lot of the problems that we humans can do every day. I'm going to show you a quick slide of activities that are going on. My laboratory has been building these complex robotic systems for some time. As a matter of fact, for the last 20 years. On the left side, you see humanoids that we actually build. We don't purchase them, we build them. And that brings sort of a new dimension. On the left lower side, we see an exoskeleton system. Those are designed for worker augmentation, in particular in transportation, in logistic operations, and there is a connection for also worker safety, muscle safety, and also even the safety in the environment as a whole. On the center, we see a new trend of robotics, more in our city environments, where we are seeing a proliferation of these systems, whether it's a healthcare or whether it's just in our cities, transporting and maintaining facilities and buildings and so on, outdoors, indoors, and so on. And those are going to just increase their number. And we need to explore what is the interaction with the people and how people feel about using these systems. And another important aspect here on the right side, aside for if you have some engineers in this room, you might be familiar with dynamic systems and controls. Ability of walking is a difficult task. That's things that we work on. But on the lower right, we see what we call psychophysiological sensing or physiological sensors that we manufacture here at UT, at the University of Texas. And those are trying to assess how people feel, the stress levels, and the mental workload, and the reaction times when we operate these kind of systems, if you will. So building human-centered robots and humanoids is a difficult task. My group built with NASA the robot in the center. You can see it performing a very complicated task where he's opening doors, removing bags, putting a bag on a containment vessel. It's interesting, this is NASA, but this particular research was paid by one of the divisions of counterterrorism. There is synergies between NASA and some of the agencies. Often we show these videos, but when I talk to younger people, younger generation, I want to tell them that they should not focus on the complex machine. We start really simple. We start with these devices on the left and the right. Those are called actuators. And those are simpler units that the students and younger people can focus on at the beginning. In here we have an IP, a patent that we had, where we're driving what is called a ball screw, which drives a ball nut that goes inside the casing as a piston-like drive. And it has novel materials, special rubbers with viscoelastic properties. We have liquid cooling. These are the kind of things, and it has a motor, obviously, an electrical motor. It can be a hydraulic motor as well. And those are sort of the essence of these humanoid robots, that they contain a lot of these devices, and that power the movement and hopefully makes them as versatile as we wish. Together with that, we deploy these robots and we deploy them for days and weeks and so on, repeating over and over the task, trying to see what levels of autonomy they can deliver. So here on the bottom part, we see a succession of tests of repeating the same task from end to beginning to end, and the number of successes and the number of failures. The number of successes are the green dots, the green boxes, and the failures are the other ones. The failures can be software bugs, can be perceptual bugs, can be estimation errors. It can be balance errors. So you can see that we are about 50%. And that's pretty much where humanoids are today. We are still trying to comprehend. It's one of the most difficult engineering sciences, if you will, trying to comprehend how to operate these robots properly in our environments. Thankfully, there is a myriad of new technologies involving augmented reality, involving different objects that appear virtually, and then superimposing them with the reality of the environment allows operators to be extremely effective and spending what we call cognitive workload to a lesser degree. And this opens opportunities that single operators, whether it's in the space or here on Earth, wherever it's environment, right, could be operating many of these robots at the same time, right? That's the future that we envision for scaling certain types of operations. Here you see more pictures showing the subtleties and of interacting with environment. And although there are great progress on autonomy and AI, these operations cannot be done 100% autonomously. An operator still requires in the loop, and probably is a good thing because we need the operator judgment wherever we go. So I'm also co-founder of a company called Aptronic here in Austin. We build humanoid robots, such as the one on the left side, called Astro humanoid. It has these anthropomorphic hands. It can be teleoperated, but has also some degree of autonomy as well. We build a QDH, a quick development humanoid on the right side. It looks very much like these Boston Dynamic humanoids. And those are becoming increasingly more popular, especially in the US. You've seen Tesla, you've seen Boston Dynamics, and there are new companies, figures. Lately, Microsoft is getting into, it might get into humanoids as well. And there is all these new opportunities for these robots as economies of scale are kicking into the manufacturing of this type of machine. So it's very, very exciting. Other ventures we have had together with companies and the pairing of a company and academia and nonprofits is very important. Has been on the area of strength augmentation or strength amplification of workers carrying heavy weights and being able to maneuver in the environment. For instance, it could be firefighting. They might have to carry heavy protective equipment or tools to mitigate fires. And that brings us to fundamental questions on the comprehension of the human body, in particular the musculoskeletal system as a dynamical system, because we need to couple the machine, man-machine interfaces at the muscular level, if you will. So that's a work that we did for transaction neural system organization engineering, where we study nonlinear models of neuromuscular behavior, ways that muscles are very unique. It turns out that we humans don't operate at all, obviously, as machines do today. But by comprehending the human neuromuscular system, we can make better robots, and robots that are they're safer, more natural, interact better with us. The vision of this sort of exoskeletons is normally logistics and construction in any sort of environment, including space and firefighting as well. But one of the notes is that there are 500,000 worker accidents in the US alone every year, a lot of them because of injuries, just muscle injuries, carrying too much weight and so on. So we expect exoskeletons to reduce fatigue, but also a lot of the accidents happens because people fall from ramps, they fall into pit holes, they run into machinery and so on. So exoskeletons can be also used as a guidance tool, and those opens really exciting industrial areas of exploration. Finally, I'm part of this global effort at the University of Texas called Good Systems, where we operate at the intersection of the social, engineering, and computational sciences. We have 7 core projects, and I'm one of the co-leads of living and working with robots. But there is other important impending sort of topics that we need to address for these human-centered robots to be effective, in particular, things like AI and racial justice, disinformation, privacy with being watched, the use of these systems in the smart cities, smart hand tools as a whole. What's the meaning? What's the use? Does this democratize or not these technologies? That we explored at the whole UT level with people from many different avenues of knowledge and expertises. Thankfully, we opened recently a new large building. It has 30,000 square feet of laboratory space. We share equipment. It's just a fascinating place that we invite everyone here to come over and explore the facility. So towards these sort of good systems projects, it is important to bring together the expertise of many different avenues of knowledge. So we have in this project a growing convergent research and a National Science Foundation National Research Traineeship and this Living with Robots project. We have about 17 faculty with expertise in communications, in data informatics, in journalism, in advanced computing, in urban design, plus computer science, obviously, sensors, and so on and so forth. And it's that blend of people together that brings together studies, in particular addressing the use of robotic systems in public spaces. For instance, can robots take public transportation? Can they go to an entertainment value? Can they be in a very crowded space? So here in the bottom right side, we see an example of these studies with two concerns that we have. On the left side, we have what we call robot encounters. If these robots proliferate in our environments, how people feel about being with these robots. So we call these encounters. How do they feel if there is a great number of these machines around? How do they feel as a sort of a question and team science perspective? But how do they feel at a physiological level? And that's why we use sensors such as electroencephalography sensors and what we call electrodermal sensors, which they measure sweat and level of stress. And here on the right side, we have the other side of the question is, what kind of level of supervision do we need to monitor and assure safety of the systems? And what is the ability of operators to maintain attention, to reduce mental fatigue for a number of hours? We're trying to, in other words, envision cities and setups, and perhaps in a space as well, where there is an equal amount of robotic systems and people, and how can we make sure that people feel comfortable around these systems? I'm going to skip this quickly, but these sort of studies are very comprehensive. In particular, we're looking into what we call convergence data models. We're collecting a lot of data, and I'm not talking about data about the privacy of people. I'm talking about data of infrastructure, digital twin data, and yes, reaction of people, anonymous reaction of people, in order to give recommendations and train AI systems for these robots to be more effective in our environments. And then we explore, other areas. Autonomy is very important. What we call community factors is very important. It is a true fascinating type of project. The origins of these projects dates back to the beginning of the pandemic, where we envision robots moving inside our building autonomously. What you're seeing here on the upper right side is robots that are completely autonomous, and they're able to go into these incredibly narrow spaces. And with using just RGB information, camera information, being able to figure out in which ways they have to navigate, respecting the spaces and without colliding. These are new avenues that are now enabled by deep learning. And in particular, our flavor of approaching these problems is using something called behavior cloning, in which we have people basically driving instrumented cars around the facilities, and we're taking days of data, hours, and in many environments, and we're training these sort of neural networks in order to imitate the behavior of people. That's a very good way of being able to learn from humans. But obviously, simultaneously, we need to develop modalities where we can understand what is the impact on people when we use this system. So the use of physiological sensing modalities. In here we see epidermal sensing with these electrodes on the skin that measure sweat. We see these electrodes on the head. They are very succinct, very easy to wear. We can measure cognitive load. Those are routinely used in these kind of projects in order to understand the magnitude of the impact of mental workload and comfort of people.
Professor Sentis, can you hear me?
Yes, yes.
So we are so excited, and we really appreciate. I think we're far over the time, so I just wanted to let you know if you had any final words and how we can get in touch with you.
Yeah. So absolutely. Let me just stop the presentation. And I mean, maybe I think that just wanted to show maybe one of the important areas of the lab, which is humanoids and the ability to learn to perform tasks. You can get in touch with me through the Human Centered Robotics Laboratory anytime in the near future. I know you're in a tight schedule. Thank you so much for inviting me today.
Thank you so much.